Okay guys, this is chapter 9, section 1. Let's go ahead and try this warm-up. This warm-up is a very challenging warm-up. Make sure you think carefully through it. This is off a state exam, and it's not easy. It's actually kind of tricky if you don't read through it carefully. Alright, so the dimensions of the bigger square, can't see it that well down here, but it's really x by x. The hard part is to figure out what the dimensions of the small square are from here to here. If you read this carefully, it says it has a 2-inch border. So for the 2 really represents the thickness of the border. So in other words, it means that the length of this smaller square is really the length of the larger square, which is x, minus this piece down here, which is 2 inches thick, and this piece up here, which is 2 inches thick. So from here to here is x. If you cut off this, that would be minus 2. Cut off another 2, that'd be a total of minus 4. So that means from here to here, the length of the small square is x, the full length, minus 4. That's the hard part, guys. So that means the dimension of from here to here is also x minus 4 because we have been told that we're dealing with a square within a square. If they want me to find the total area of the border, that really means you have to find the area of the bigger square, which is x by x, which equals x squared. Then you have to find the area of the little square, which is x minus 4 by x minus 4. Okay, or if you want to look at it this way. So x minus 4 times x minus 4, because it's side times side. This is going to force us down to the distributive property FOIL. First would be x times x. Outers would be x times negative 4. Inners would be negative 4 times x. Last would be negative 4 times negative 4. Combine your like terms. That gives me x squared minus 8x plus 16. So this right here is the area of the big square. This right here is the area of the small square. In order for me to find the area of the border, I have to take the big square and subtract off this to be left with just the white space around. So the area of the border is equal to the big square, and you have to subtract the small square, which is represented by the whole trinomial. So you've got to put that in parentheses to subtract the whole thing, which forces me to distribute a negative 1 through that. That's going to be x squared. Now distribute. Negative 1 times that would be x squared. Negative 1 times negative 8 would be positive 8x. And negative 1 times 16 is negative 16. The x squareds are going to cancel. Therefore, the area of the border is equal to 8x minus 16. Really tough question. Make sure if you don't fully understand that, rewind and listen to this again, okay? Alright, 9.1, we're now getting into quadratic equations and their graphs. A quadratic function or equation is a function that can be written in the form of y is equal to ax squared plus bx plus c, where a is not equal to 0. The form is called standard form of a quadratic equation. These are all quadratic equations. This is the parent function or the standard form of any quadratic equation. Okay? Make sure you put it in standard order, which means highest exponent to the least. Anytime you guys see a squared, it's going to indicate that it's a quadratic equation. Okay? If it's a quadratic equation, that means it's going to form a parabola. Now, when I just put it into pen mode, I lost the bottom part of my PowerPoint. So what the bottom part of the PowerPoint said, that if a was greater than 1, then that means your parabola is going to open up. If a is less than 1, that means your parabola is going to open down. I'm sorry, it's supposed to be 0. Okay, so if it's positive, it opens up. If it's negative, it opens down. Now, a is this right here. That's what they're talking about with a. It's the leading coefficient in front of the x squared. This equation right here is a quadratic equation. The problem with it is it is an incomplete quadratic. It's got the ax squared. It's missing the bx, which would be 0x, plus the c. So if you looked at it like it was complete, this is what it would look like. They're not going to put in the zeros. This one's missing it's got the 1x squared. It's missing the bx, so that would be 0x, and it's got the c, which is the 9. This one is complete. The a is 1, the b is -1, and the c is -2. So 2 of them are incomplete, 1 is complete. All of them are quadratic because they are squares. All right, so let's look at what a parabola looks like on a graph. The axis of symmetry, you guys can just draw a sketch graph for this. We'll get to a real one you're going to need graph paper. But the axis of symmetry for a parabola is actually the dotted line that breaks the parabola in half. So for example, it would be right here. Whoops, I'd actually like to, hold on a second, let's change the color on that so it's a little easier to see. So that dotted line breaks this parabola in half so that it's symmetrical. This right here is called the axis of symmetry. Okay, so that's the axis of symmetry. In this example, the axis of symmetry cuts through the x-axis at -1. So this one would be x equals -1, if you can see that. That would be the equation for that axis of symmetry. The vertex is actually where the parabola takes a turn in direction. So as the parabola is going up, it's starting to curve, it hits a maximum point, it turns, so it's right here, and then it comes back down. So the maximum point in this parabola is the vertex. The formula that you guys need to know, which actually is somewhat hidden in your reference sheet under the quadratic formula, is -b/2a. But you have to know that this formula belongs to the vertex, which is the turning point of your parabola. Now, the turning point, the vertex, can be either a minimum or a maximum. So if your parabola opens up, then your vertex is a minimum. If your parabola opens down, then it's a maximum. So it can't be both. It's going to be one. Your vertex is either going to be a minimum or a maximum. Okay? Now your domain is on the x values of the axes. In this case, if you look at this, no matter what, understand that this parabola always curves out. It never goes linear. It constantly goes out, out, out. So if you look at the x-axis, it means that no matter how long I draw this parabola, it's always going to hit. Like if I go out to 4 next axis, I go way down, it's going to hit way down. So it doesn't matter how far I go out. In this example, the domain would be all real numbers. Whereas the range, which is the y, the minimum point the maximum point it hits is at 1, 2, 3, 4 right here, so it's at 4. So the highest point of this parabola has to be less than or equal to 4, and then it goes all the way down to infinity, negative infinity, and the symbol you guys may already know for negative infinity is a sideways 8. So that would be the range for this particular example. Okay? All right, when you're comparing widths of parabolas, this is actually kind of an observation problem, and we have snapshot pictures of a graphing calculator to show it to you. When A, and these are all incomplete quadratics, but when a is equal to -4 versus a is equal to 1/4 versus a is equal to 1. Notice that both of these are positive a's, so both of the parabolas should open up. Whereas this one is negative, which means the parabola is going to actually open down. Okay, so that's the first observation you should be able to make. The second observation is that when you compare the two positive a's, notice that if a is smaller than 1, then it goes wider. So if a is less than 1 but greater than 0, then the parabola is going to end up being wider. If the a is bigger than 1, then the larger this number gets, the more narrow the parabola becomes. So if I change this to like a 5, that would make the parabola much more narrow. If I change this to a, I don't know, say 1/100th, it would make it extremely wide. Okay? Now, if you can't remember all these rules, don't forget, I've said this 1,000 times, you guys can always go back and build an XY table and put in your -2, -1, 0, 1, 2, and plot your points and figure it out that way. Okay, so let's go ahead and do an example. It wants us to graph the parabola and identify the vertex. Let's go ahead and do question number 4. So get your graph paper out, get that ready to go. I'm only going to do one of these. Graph paper is pretty essential, so I've got about, looks like 3 minutes to complete this. So the first thing I'm going to do is I'm going to identify this is an incomplete quadratic. It's got my ax squared, it's missing my bx, and it's got my c. So a is equal to -2, b is equal to 0, and c is equal to -1. All right, also notice that a is a negative. Because a is a negative, we know that the parabola is going to open down, and it's going to have, the vertex is going to be a maximum point. So let's figure out what the axis of symmetry is. So that's the x equals -b over 2a formula. Plug in -b, b is 0, divided by 2 times a, which is -2, which is 0 divided by -4, which is 0. So the axis of symmetry, grab a straight edge, is going to be at 0, which is right smack on top of the y-axis. So this is x equals 0. Now, to find the vertex, we have to substitute, watch carefully, we're going to substitute 0 back into the equation, the original equation. So y is equal to -2 times 0 squared minus 1, back into this equation right here, which is equal to 0 squared is 0 times -2 is 0 minus 1 is -1. So the vertex is 0, -1. So find 0, -1 is right there. Okay, in order to figure out some points, you're going to have to build a table. The trick is to take the vertex, which is right here that you just found, and put that in the middle of your table, because the vertex is your turning point. So put that in the middle and then build some numbers below and build some numbers above. So guys, when you put in -2, you're going to get -2 squared is 4. 4 times -2 is -8. Put in -1. -1 squared is 1. 1 times 2 is -2. Put in 1, you get 1 squared is 1 times -2 is -2. And put in 2 squared is 4, and 4 times 2 is -8. Notice these guys are the same. That's because it is actually symmetrical. So when you plot these points, it's going to be off. They're going to be symmetrical. Whoops, right here and right here. And I'm going to run out of time, but go ahead and graph it. Whoops. Put arrows and label, and then you'll be done with this problem. Okay, we'll do more of these though, so don't panic on it too much.